Hello, everyone. My name is Heye, and I'm a project leader for laser development at Class 5 Photonics. Class 5 Photonics is a spin-off of the laser group of the German electron synchrotron facility DESY, based in Hamburg. And we at Class 5 are serving the ultra-fast laser market with our customized solution for more than 6 years already now. Today, I want to talk about actually two of our OPCPA systems. One is announced here in the title. It's running at 1 megahertz, offering few cycle CEP stable pulses, and it comes with a dual channel output centered around 800 nanometers and 2 micrometers in wavelengths. The second system is based on the same design, but comes at slightly lower repetition rate, 200 kilohertz, but therefore can offer higher pulse energies and output up to 15 microjoules of output power. Both systems are from the design passively CEP stabilized. The 1 megahertz has additionally an active control. But let me jump into the laser design. So the systems both are using diode pumped femtosecond industrial lasers with a central wavelengths around 1030 nanometers. And this laser sits on the same water-cooled breadboard, so they have the same housing, and that offers a great stability for our OPCPA systems. For the configuration A high repetition rate system, we use the Coherent Monaco running at 1 megahertz, 60 microjoules of total pulse energy, and pulse durations of less than 300 femtoseconds. For the configuration B, which I call now the high pulse energy configuration, we use a light conversion carbide running at 200 kilohertz, 200 microjoules of pulse energy all in, and also similar pulse durations of 300 femtoseconds. That both lasers have similar pulse durations makes our lives easier in preparing the dispersion management for both systems, which is a nice side effect. Both systems can offer a third output where we basically route the 1030 light out of the pump laser through our box so that the customer, if he wants, could also use the direct output of the diode pump industrial laser. Okay, but now let me come to the OPCPA design. We're splitting off a small fraction of 1 microjoule to generate a broad white light in the visible and in the red part around 1030 nanometers in a crystal-based white light generation process. A typical spectrum looks like this, which is just shown here for the 1 megahertz setup. So the white light starts spanning at 550 nanometers up to 950 nanometers and is then subsequently frequency mixed to a CEP stable idler by adding around 500 nanojoules of 1030 nanometer light. So the output of this DFG stage offers a passively CEP stable seed for the next stage, starting around 1.6 micrometers and spanning up to 2.5 micrometers, which is then further amplified in a non-collinear OPA stage, pumped by 28.5 microjoules. And we here already reaching above 1 microjoule, for example, for the 1 megahertz system. So that corresponds to more than 1 watt of average power with a good power stability of 0.2% root mean square, which is shown here for measurement for more than 14 hours. The spectrum is a little bit narrower than the CEP stable seed. It's roughly centered around 2 micron and has a nice round beam profile. We have already so much power here, and we don't need it for the next white light generation step that I will talk in a minute about, that we can use a fraction of that light and bulk compress it, which we have done here in fused silica, and we achieve central wavelengths 2 micrometer, sub 40 femtosecond pulses. A frog trace is showing here where you see that they are only TOD limited due to the bulk compression. But for sure, if in the next step we would use customized chirp mirrors, you would have a bandwidth of less than 35 femtoseconds compressed here as a second output. For the main application for the system, we use the CEP amplified light around 2 micron to start and generate a second white light, which is then offering also CP stable photons. And a typical spectrum is showing here. It spans roughly between 600 and 1 micrometer, 600 nanometer and 1 micrometer of spectral range. And the CP stable light generated by the CP stable 2 micrometer light is then used in a subsequent stage to be amplified further, that we achieve an 800 nanometer central wavelength CP stable pulse for output 2. To do so, we use for configuration A 30, the remaining 30 microjoules, or for the configuration B, the remaining 170 microjoules in a standard SHG stage, which corresponds to either 50 microjoules in configuration A or 90 microjoules in configuration B, and pump then another non-collinear OPA stage, which amplifies the CP stable 800 nanometer seed from the white light generation 2 process further. And I will show now first data for the 1 megahertz repetition rate or high repetition rate system. So at the output around 800 nanometers, we achieve again a good stability of more than 0.3% root mean square, running on 1 megahertz, again measured for more than 14 hours. We have a broad spectrum corresponding or offering a bandwidth for a sub 9 femtosecond pulse. And also we achieve again a nice round beam profile. The high repetition rate configuration here comes with an active control for the CP stability. In that case, we show some data where we use an external F2 interferometer to determine the CEP spectrogram. And on the left side, for the first 30 minutes, we let the system run with the stabilization off. And when we turn it on, we basically end up with this, in this case, corrected CP or actively corrected CP phase around 174 millirad root mean square. But we see also that the noise in both systems or in both configurations, sorry, is pretty similar. So here we assume that we are already at the detection limit of our F2F interferometer, and the active control allows to keep it stable without any further phase drifts. If you look at the data for configuration B, which is the high pulse energy configuration, again, we have a good power stability of 0.3% root mean square, running at 200 kilohertz. Here, the measurement spans over 25 hours, just for comparison. We have a nice ellipticity around 0.94, where 1 equals round, and the spectrum is very similar to the spectrum of the 1 megahertz system. This system is only passively CEP controlled. I will come to that in the next slide. Here, I also want to show some M-square measurements showing a good M-square of below 1.2 for both spatial erections, and also you can see a plot of the beam caustic on the right side. For pulse compression, we used here the D-scan from ultrafast photonics, and we get a nicely compressed pulse below 9 femtoseconds, which is shown on the lower right side. I also want to show some F2F spectrograms, which were measured with in 10 millisecond steps at a 100 hertz frequency, and for 10 minutes. And you see the passive CEP is pretty similar to the value we achieved before in the other system, ending up at 167 millirad root mean square for a 10-minute carrier envelope phase jitter. And we think for a passive system, that's already a pretty good and workable value. So let me get a combined overview of the systems. I presented today two systems, one running at 1 megahertz, offering 1 microjoule pulses, very stable pulse stability below 0.3% root mean square. And we have a similar design for 200 kilohertz high pulse energy output B, which offers more than 50 microjoules of pulse energy. And both systems come with short pulses of below 10 or actually 9 femtoseconds. One system A is actively CEP stable, and system B comes with a passive CEP output, both ending around 170 millirad root mean square in measurements. These systems are both offering dual channel outputs if needed. We can also compress the 2 micron to a Fourier limited pulse around, let's say, 35 femtoseconds. And these channels are available at the same time. So there's a dual use, really a dual use. It's not switchable. With that, I thank you very much for your attention. And if you want to get in touch with us, we are available through all more or less social media channels. We have a YouTube channel. If you want to get more information, you can get updated on Twitter. And as usually, we are accessible by LinkedIn or Classic by email. So thank you very much. I hope you all have a great online conference, and I hope you will reach out to get more information from us at Class 5 Photonics. Thank you very much.